Thank you. I will probably be faster. So today we are going to talk less about physics and more about engineering. My talk is indeed about quantum cryptography, or more precisely quantum key distribution, and I am going to speak about its certification for the quality of its commercial implementations. My talk is divided into two parts. The first part is a tutorial. In case you are not quite sure what quantum cryptography is, I'm going to tell you. And then in the second part, I will tell you about my actual latest research results. So let's go on. Before we talk, am I clearly audible, by the way?
Yes.
And when I move my mouse, do you see my mouse?
Yes.
Sure. So let's talk about cryptography first. We all use cryptography every day. Anything that involves money, involves communications, anything that involves computing gadgets, everything we touch and do uses cryptography. This is kind of hidden from us, so if you don't think about it, it's very easy to miss. But basically, all the updates your computing gadgets receive are digitally signed, so cryptography is used to ensure the integrity of the update. Anything, all your communications are encrypted, voice, online, you go to the website, it's most likely encrypted. You make a phone call, it is encrypted, and so on. And anything that involves money uses encryption. Even if you use cash, the store, the cash register uses encryption to connect to the bank, and so on. So everything uses encryption. And there are also more traditional uses for encryption. Encryption is used in commerce, in government affairs, in military. It's also used in healthcare, commercial secrets, private life. So it's a very important part of our life, and we literally are all reliant on it. The ability to encrypt our communications make our life more efficient. By the way, should I speak English? Because I can deliver a talk in Russian if there are no English-speaking persons. If every person in the audience is...
I think we have international participants, so we request you to speak in English, please.
For sure. No problem. So we all rely on cryptography, and our society is really more efficient because we can use cryptography. If our society, the human civilization, suddenly lost the ability to communicate securely, it will be a big step back. And we will suddenly have to go to a bank to do a physical signature for every transaction. We cannot so conveniently get updates for our software, and all life will slow down. So it's important to keep this ability. But what does it take to keep the ability to communicate securely? The human civilization had the need to communicate securely since at least 2,000 years ago. At least as known from the written sources, maybe the need for longer. And if you look at a very short version, a very condensed version of the history of cryptographic systems that you see on the screen, you see that it started with simple ciphers that could be made with pen and paper or stylus and a clay tablet, and moved to more and more complex cryptographic ciphers. And the first cipher, as known in written record, was its so-called monoalphabetic cipher or scissor cipher. And it was, according to written sources, invented by the Emperor Julius Caesar. And that's a very simple cipher. It takes an alphabet. The Latin alphabet has 26 letters, and it agrees the cryptographic key, the encryption key, is the number of positions by which every letter should be shifted. So, for example, if the shift is 3, then letter A becomes D, letter B becomes E, and so on. For decryption, if you know this shift you need to do, you can decrypt the message by shifting it back by the same number of positions. And this cipher served the humankind for surprisingly long, actually at least 8 centuries, until an Arab mathematician, Al-Kindi, invented statistical analysis essentially, and showed that this cipher is very easy to crack if you analyze the frequencies of letters. because different letters in the alphabet in a text, they occur with different frequencies. And so you can very easily guess if you have an encrypted text of any significant length, it's very easy to guess which letter is which. So more complex ciphers were invented. Now the cipher changed for every letter, but still it took a slightly more involved cryptographic analysis, statistical analysis to crack dot. And then it moved on and on. And in the middle of the last century, the ciphers became too complex to be done by hand, and electromechanical machines got used. There is a very famous encryption cipher called Enigma cipher, used by the Allies in the World War II, sorry, not by Allies, but by the Axis, the Germany and their allies in the World War II. And that cipher, unknown to the Germans, was cracked by the Allies, by Polish mathematicians and American, British mathematicians. So the Allies read most German military communications, and the historians agree that this shortened the course of the World War II by a couple of years, if not changed its outcome. So the encryption is very important. The Germans never guessed that they were cracked. Nowadays, we use computers to do our encryption. So the ciphers are so complex that they contain so large number of operations that you need a computer to execute them. And nowadays, all your communication today is protected by this pair of ciphers: public key cryptography, RSA, and symmetric cipher advanced encryption standard. So right now, every computing gadget has those two ciphers installed in software and sometimes in hardware. And we are in a unique situation. We already know that one of those ciphers will not withstand the advent of a general purpose quantum computer, because Peter Shor has invented the efficient algorithm to crack Shamir-Adleman public key crypto on a quantum computer. And this is known for since already 30 years ago. So we need to replace one of those two ciphers. And the classical cryptographic community comes up with public key cryptography that we don't yet know how to crack with a quantum computer. So this is one important development. And by the way, this symmetric encryption is not very much threatened by the quantum computer. So it's just the public key cryptography that is threatened. But you need both to efficiently encrypt everything. And is this generally a fine situation? Look, every time the cipher is cracked, a new technology for cryptanalysis is developed, we replace our cryptography with the next generation of cryptography. Seems to be okay, because what's the problem if your credit card number is decoded in the future? Not a big problem. The bank has given you a new credit card number by that time. Or your today's emails, most of them have no long-term value. So what's the problem with this approach? If you are today using a cipher that today is not yet known how to crack it, then your today's communication is secure. But what an attacker can do, she can record the encrypted traffic and simply store it until in the future a decryption technology becomes available. On the picture you see a large American data center where they store, you can be sure, they store a lot of encrypted communication there for future decryption. And you can be sure many other large countries also have such data centers. And this is okay for a large part of our communication because it doesn't require long-term protection. But there is a certain significant fraction of communication that actually requires long-term protection. What about your medical secrets? They need protection for possibly for longer than your lifetime, genetic problems or whatever. Financial secrets, love letters, private communication, certain classes of types of private communication that need long-term protection, and of course military, government secrets, commercial secrets. So there is a significant fraction of communication that actually needs long-term protection. And then this is a problem. So today we are using this cryptography that we know fails when the quantum computer is built, and that can be quite soon in the future. So we cannot guarantee the required term of protection for our today's encrypted communication. So actually we need to rush to replace the system, and it's already too late to upgrade our cryptography. A good question is, can we get rid of this constant replacement cycle, and can we invent cryptography that is unbreakable in principle? And so using it will solve the problem once and forever. There are two important inventions in the history of cryptography. One is the one-time pad. It's a very simple cipher. I hope you know it. And it has been proven to be, in principle, unbreakable by Claude Shannon in his information theory. The cipher it's simple, but it's not very practical because it requires a large amount of secret key, and the secret key is difficult to distribute. So it's used, but used only in most important communications today, like diplomatic channels. And another invention in cryptography is quantum cryptography. And this is a radically new kind of cryptography. Its security is not based on the assumption that we don't yet know how to crack it, or we have limitations of our computing technology. The security of quantum cryptography is based on the laws of quantum mechanics. So essentially, its security is based on Heisenberg uncertainty relation. But it's impossible to fully learn about a quantum state that you don't know about. And by measuring a quantum state, you change the state. And the security of quantum cryptography, in theory, is strictly proven. So no assumptions. If quantum mechanics is correct and full theory of nature, then quantum cryptography holds. In theory, the protocol is impossible to break. But we'll see later what weaknesses it has in implementations. So let's talk about quantum cryptography. In quantum cryptography, you can do different things, but one of the most important things that quantum cryptography does today is key distribution. So how can we use cryptography to encrypt and decrypt messages that you want to transmit over an insecure public channel? The first thing, Alice and Bob, so Alice is the sender, Bob is the receiver, standard names for parties. The first thing they need to do, they need to agree on a shared secret key. So somehow Alice uses a random number generator, generates a random sequence of zeros and ones, and distributes this sequence, this key, to Bob in such a way that nobody else can learn the key. So some form of a secure distribution channel. Once Alice and Bob both have a copy of this, each has a copy of the secret key, and they are sure nobody else has that secret key, they can use this key in a symmetric cipher to encrypt and decrypt messages with high throughput. And then this is a classical cipher, and they use classical channel. So the easy part of this scheme, encryption and decryption scheme, is the symmetric cipher. We have good symmetric ciphers. You can use AES, advanced encryption standard that is not very much threatened by the quantum computer. Or if you are paranoid, you can use one-time pad, which is an unbreakable symmetric cipher. For that, you need a lot of key, but if you have the key, you can use one-time pad. So this is the easy part. The difficult part of cryptography is distributing the secret key, because for an Alice and Bob that cannot physically meet, and most communications are distant, you never meet the other counterpart, they need to use a communication channel. And any classical communication channel is in principle insecure, because classical information can be copied precisely. So if Alice sends to Bob classical secret key, then an eavesdropper can take a copy while this key is going through the classical channel. Today, this task of key distribution is solved by public key cryptography. This is a very particular kind of cryptography that allows, by making an assumption that we cannot perform certain computations efficiently, it allows Alice and Bob to establish a shared secret key over a public channel. But we know that public key cryptography will be broken by the quantum computer. So it's not a very good kind of cryptography. And what quantum cryptography, the first thing it offers to do? It offers to distribute a shared secret key over an insecure communication channel, a channel that is open for eavesdropping. And the laws of quantum mechanics guarantee that any attempt to eavesdrop on this transmission will be detected, will be revealed to Alice and Bob. So before they use the key, they know if the key has been attempted to be eavesdropped on. And Alice and Bob, they can use photons, single particles of light that fly long distance in Earth conditions without interacting much with the environment to actually, and they encode bits on states of single photons, and they use an algorithm to do this key distribution securely. So let's see how Alice can send to Bob a secret key that is impossible to eavesdrop on. Alice can use polarization states of single photons. So she prepares a single sequence of single photons and picks for each photon one of the 4 states of polarization: horizontal, vertical, or 2 diagonal states. She picks them at random, and each photon is prepared in the state she has randomly picked. Bob, in turn, tries to measure each photon in one of the 2 measurement bases. So either he tries to distinguish between horizontal and vertical polarization, or he tries to distinguish between the 2 diagonal polarizations. And as you all are versed in quantum mechanics, you might recognize that those are the 2 incompatible measurements. If he does this measurement and the photon was actually encoded in diagonal polarization, the moment he measures, he gets a random measurement outcome, and all the information about the original polarization of photon is lost at that moment. So, for example, if the first photon was prepared in diagonal polarization, but Bob made a mistake and he randomly measured it in a vertical horizontal polarization, he gets a 50-50% chance that he measures vertical or horizontal photon, and the measurement actually changes the polarization. So the traces of the diagonal polarization are lost. And this is, as far as we know, how the nature works on a microscopic scale. So you lose information at this point. And when Bob measures a photon in correct polarization, then he always gets the correct polarization. What does the... So how can Alice and Bob extract a key out of this transmission? After Alice transmits to Bob a large number of photons, they both record. Alice records, remembers in which state she has transmitted, and Bob records what basis, measurement basis he used, and what was his measurement outcome. After a transmission of photons is completed, Bob tells to Alice which basis he used for each measurement, but not his outcome. The outcome stays secret, only the basis is revealed. In half the cases, randomly, it turns out that Alice prepared the photon in a basis that is not the basis in which Bob has measured it. Unless Alice and Bob did not know that Bob's measurement result was random, and they threw away those bits, discard half the bits of the key. In the remaining half the cases, their preparation and measurement basis matched, and they both know that Bob measured the same polarization as Alice has prepared. And those bits can form a shared secret key if they both agree that one polarization represents bit 0 and the other represents bit 1. Why is this key secret? What if somebody, that somebody is called Eve, tries to eavesdrop on the photon transmission? At the time of photon transmission, Eve does not know in which basis Alice prepared the photons. That is going to be revealed later. Neither does she know in which basis Bob is measuring each photon. That is also revealed later. But she has to measure the photon now while it's flying through the transmission line. So she also has to guess. And she half the time picks the basis improperly. Picks a wrong basis. And she gets a wrong measurement result. But after measuring the photon, Eve has to regenerate the photon and send it on to Bob. If she doesn't recreate the photon, then Bob would think that the photon is lost to the losses in the transmission line, and Alice and Bob will simply not use that bit. And it's okay if most photons get lost, real transmission lines are lossy. If Bob did not receive the photon, this is okay. They only make the key out of those photons that were actually detected by Bob. So it has to recreate according to her measurement result. And by doing that, she will introduce errors. So when Bob measures the same photon, but in a correct basis, the same as the preparation basis by Alice, he will get wrong polarizations because Eve failed to detect that photon on a correct basis. And she fails half the time. So any attempt of measure those states of polarization introduces errors in the shared secret key between Alice and Bob. They can check for that, of course. They can pick a random subset of this key, publicly reveal this random subset, and check for discrepancies. And if they see errors in the key, this means somebody has tried to eavesdrop that key. And if they don't see errors in the shared subset, then this, with a high probability, means that nobody has eavesdropped on the remainder of the key. Then they can use the remainder of the key as the secret key. So this is, in essence, the principle behind every quantum key distribution protocol. There may be 20 of those protocols, but they all rely on the principle that a measurement of an unknown quantum state changes that state. Now we look how the protocol works in practice. So Alice and Bob, indeed, they exchanged photons, and most of the photons got lost in the lossy transmission line. Some of them are received by Bob. And after this photon transmission is done, Alice and Bob communicate over another communication channel, a classical communication channel, which can be any classical channel, for example, internet or a radio channel. And then they do post-processing to extract the secret key. The first thing they do, Bob tells to Alice over this classical communication channel, and that's an unencrypted channel, by the way, you can listen to it, which photons he managed to receive and in which basis he received it. And Alice then discards all the photons that Bob has not, all the states bits that Bob has not received, and also discards all those instances when Bob picked a wrong measurement basis. So what remains is a sifted key, the key where Alice and Bob detected a photon and he detected it on a correct basis. Now, in the absence of equipment imperfections, that would be already the shared secret key. But actually, even in the absence of eavesdropping, there are some errors in this key because equipment is not perfect. There is no such thing as 90-degree polarization. It's always a bit less or a bit more. Bob's detectors have dark counts, they have noise. There are various imperfections in the scheme. There's might be some stray light in the line, communication line. So in short, the key, the sifted key, contains a few percent of errors generally. So Alice and Bob, they use a classical error correction algorithm. So they exchange some extra information over the classical channel and they correct all the errors in their key. In the process of error correction, they also learn the exact number of errors in the key. So they receive an error-corrected key, and they know how many errors there have been in the key. Then they have to conservatively assume that all the errors in the key were because somebody tried to eavesdrop. And they look at the security proof. It's quite a complex mathematical derivation that tells them what is a possible amount of information the eavesdropper could have obtained if there are so many errors in the key. So under this conservative assumption that all errors are because of eavesdropping, they calculate the remaining secret key fraction. For a most common used QKD protocol, BB84 protocol, if there have been 11% of errors in the key or more, then Alice and Bob cannot extract any secret information. But if there are less than 11% of errors, then a partial secret information remains in the key. Then Alice and Bob can compress the key using hash functions. A hash function. This is so-called private simplification step. So they take the input key, and about this key, Eve can have, she call no partial information. And they compress this key to a shorter length using hash functions, and above the shorter key, if knows nothing. So they have a secret shared key, and the last but not least, they have to authenticate itself to each other. So Alice has to prove to Bob that she has been talking, it's Alice who has been talking to Bob, and Bob has to prove to Alice that indeed Bob was talking to Alice. If they don't authenticate, then somebody could have broken both communication channels, the classical and quantum, in the middle, and pretend for Alice to be Bob and pretend for Bob to be Alice, but actually sit in the middle and do two separate quantum key distribution sessions. So this is a so-called man-in-the-middle attack. And to prevent a man-in-the-middle attack, Alice and Bob have to use either a short initial shared secret to sign some messages on this classical channel, or they can rely on an updated public key infrastructure, perhaps resistant to the quantum computer, to do this first initial authentication. And after they have authenticated themselves and they have a shared secret key, then they can set aside a small fraction of this key and use the small fraction in all future authentication sessions using Vadim-Carter signature algorithm. And this is Vadim-Carter algorithm. It's in the same class of security as one-time part. It doesn't make any assumptions. It's impossible to break. So the use of this public key infrastructure for the first authentication is okay because it's forward secure. Once the authentication is done, even if the public key cryptography is broken in the future, this does not compromise this key. So there's a lot of mathematical processing, and actually most of the processing is relatively simple, the optical processing, but most of the processing is here in the digital equipment, and you need some computational resources to do all this. So all this has been implemented since about more than 20 years. For more than the past 20 years, you can buy those systems, they are commercial. Everything has been implemented, and here you can see how a quantum key distribution system looks like in a rack, in a data center, when it is installed. There are two QKD boxes, so two Bobs sitting in a data rack, and they each one connect to another node in the network, this one to one node, and another one to another remote node. They generate the key. They are connected with a single mode optical fiber. The same fiber that is used for data is also used at a different wavelength for the key distribution. They generate the key. The key is passed to a key manager who decides how to use the key, and then is passed to symmetric encryption equipment. That is with the AES cipher. It encrypts all the traffic, now classical traffic, in this network. This network uses single mode fiber. The longest link is 14 kilometers. Single mode fibers are very transparent medium. At 1550 nanometers, it has 0.2 dB per kilometer loss, which means in this 14 kilometer link, only half the photons got lost, 50% loss. So actually not much. But if you keep making this link longer and longer, the losses increase exponentially. So 14 kilometer plus 14 kilometer plus 14 kilometer, you have to multiply the losses. And eventually, after 100 or 200 kilometers, too few photons arrive to the other side. So if the link is too long, the key generation rate drops to impractically low values, which is a problem because you are not getting much key. So what can Alice and Bob do if they are separated by too large distance for a single hop? In today's technology, they can split the link into shorter segments. And if in the intermediate location there is a secure room to which an attacker does not have access, they can use shorter distance links to perform QKD. So the end user performs quantum key distribution with this intermediate trusted node. There is a separate, different quantum key distribution link to the another end user, and this node gets two keys. Then it uses one of the keys, essentially it uses key 1 as one-time path encryption key for key 2. No, that's the other way around. So it uses key 2 as an encryption key for key 1, uses one-time path, unbreakable cipher, So essentially it adds two keys together by exclusive OR operation and publicly announces the result. This publicly announced result goes to one of the users, and this user uses his copy of key 2 to decrypt back the key that has been encrypted and gets key 1. So in the end, the two remote users share the same key. This encryption, I repeat, it's unbreakable. It's unconditionally secure because Shannon has proven at one time it's unbreakable. So this can be chained more. You can make an unlimited number of those links as long as you have trusted nodes protected from outside interference. So if you trust your network provider, you can make a very long chain of key distribution nodes. This is today's technology. So this is how today quantum key distribution networks are built. In the future, we will have end-to-end security. And in the end-to-end security, you need to do efficient entanglement swapping operations, and you need to do some error correction. So it's very interesting. The proposal is there. Lots of physics labs are working on this, but essentially the technology is not yet ready for deployment. And my prediction is when we have a general purpose quantum computer, then we will have sufficiently good quantum memory and sufficiently good operations to implement those quantum repeaters. So this is future technology. In the future, this will be end-to-end. Today, you need trusted nodes. Those trusted node networks are built in many countries, more than 15 countries, including Russia, including China, including European countries, Japan, South Korea. And nowadays, in many countries, the length of those trusted node chains exceeds thousands of kilometers. The world leader in the quantum key distribution network deployment seems to be China. As of today, and also 2 years ago, they have deployed 12,000 kilometers backbone network over the entire west coast, the most populated area of China. Also, they used QKD over satellites with free space channel connecting to a quantum satellite to connect more remote locations to this network. And this is just the backbone. This backbone is connected to metropolitan networks in many cities along the way. And this, for example, this is how the metropolitan scale network in a small Chinese city, Hefei, 5 million citizens looks like. So there's 159 users, mostly government users. And the network has a topology with 8 municipal nodes to which the users are connected. And so this is a city network, and this city network can be connected to the national backbone. So this kind of networks are in many cities. Beijing, Shanghai, Jinan, and so on. And in other countries as well. So in Russia, there is backbone being built between Moscow and St. Petersburg, and there are users in both cities. All right. So this wonderful technology, it's already being deployed. And the question is, how secure is this technology? In principle, in theory, quantum cryptography protocol is impossible to crack. This is strictly proven. But the equipment used to implement this protocol is imperfect. There are many discrepancies between the actual equipment and the theoretical description of the protocol. The equipment contains about 20 optical parts, and each optical part has imperfections, or some extra properties. It has quite complex electronics, several printed circuit boards are full of analog and digital components to do all the processing between the optics and processing and the digital processor. And it has a large software code. And it has lots of algorithms like adjustment algorithms, calibration algorithms that don't even exist in the theoretical description of the protocol. The protocol is described on 2 pages of text, but the actual code that implements a commercial system is many thousands of lines long. And if you examine carefully the implementation, you can find many differences between the implementation and how the theory tells it should behave. And when you find a discrepancy, very often you can then construct an attack based on implementation imperfection or discrepancy, implementation limitation, that then breaks the security of the protocol. At present, we know about 30 of such attacks, 30 different imperfections and about 30 attacks. There's a whole catalog of them. So we need to look after implementation imperfections. The principle of the cryptography is secure, but implementation imperfections, like with any cryptography, needs to be taken care of. And if you tell a bit more strictly, in what situation we have to provide security? We have a protected room containing Alice's equipment, Sander's equipment. We have the same protected room containing Bob's equipment. To this room, the attacker does not have physical access, so it's shielded from interference. There are two communication lines, the optical communication line for photons and the classical communication channel. In the optical communication line, the eavesdropper can apply any technology that is allowed by physics. She can substitute it with a lossless line, do quantum teleportation, she has perfect quantum memory, she has a full quantum computer. Anything the physics allows, she can do. She can also put a lot of light in this communication channel and inject light inside Alice and inside Bob. This is an optical channel. She can generate this light with a laser and allow. The physics allows her to inject light. She can also do this. So anything physics allows, she can do. She can also listen to all communication on this classical channel. She cannot replace this communication because the channel is authenticated. If she replaces the messages, she will be discovered, but she can listen to all of them and she can use this information in her attack. Another assumption we have to make. We assume that Eve knows everything about the content of Alice's and Bob's boxes. She knows exactly how they are constructed. The precise description of the hardware, all the schemes, all the circuit diagrams, and a copy of the software code. She knows everything. Furthermore, we have to assume she knows all the imperfections inside the boxes. So if some component has a certain value of imperfection, a certain characteristics that varies sample to sample, we assume she knows the exact value of this particular sample used inside Alice or inside Bob. And this last requirement sounds like a stretch, because how can she know what's inside the box if and what parameters it has if she cannot have physical access to the box? And indeed, it sounds like a stretch, but the history of cryptography shows that if you don't make this assumption and you say that Eve cannot learn certain aspects of your construction, then your cryptographic system is going to be broken. So there is the time-honored principle called Kerckhoffs's principle that has been practiced at over 150 years. There are many historical examples when the construction of the cryptographic system was secret, those systems tend to be broken. So we make this assumption. So using our limited today's optical technology, we have to protect against almighty Eve that can use any future technology. That's a difficult task. Now, we are speaking about those imperfections, and I want to give you one example of equipment imperfection that can create a loophole allowing to break the QKD algorithm. In the example shown earlier today, Alice had to generate 4 polarization states. And if you go to an engineer and ask, what is the easiest and cheapest way to generate 4 polarization states? The engineer tells you, if you take a semiconductor laser, the semiconductor laser emits a linearly polarized light. So let's take 4 lasers, rotate them at 4 angles, and through a network of optical beam splitters, combine their optical output into one optical beam or fiber. And then we take 4 electrical generators and we simply put current through one of the 4 laser diodes. And this current pulse makes it a flash, produce a flash of polarized light. And indeed, depending on which laser you have activated, you get a different polarization. And indeed, this type of source works beautifully, it's cheap, it's easy to build. But the problem is, besides, it doesn't just produce 4 different polarizations. The pulses from 4 different lasers, run by 4 different signal generators, are never going to be exactly the same. They will also have difference in timing, and they will have difference in the wavelength, because there are 4 different lasers. So if you look at the timing characteristics, so those are the pulses emitted by an actual source of this type. And you see that even though they overlap, they are shifted in time. So, for example, and then what Eve can do, she can measure the timing of the photon flying through the transmission line. And if she sees that the photon is flying with this timing, she knows that this is certainly not the vertically polarized photon. That emission starts later, and it's likely one of those three other polarizations. And if she measures timing of photon and she sees that the timing is 1.5 nanoseconds relative to the reference, then she knows that this is twice as likely to be vertically polarized photon than any other three. So by measuring timing of the photon, not measuring polarization, she only measures timing, doesn't touch polarization, she learns probabilistic information about polarization. And she doesn't introduce any errors, because physics allows her to do timing measurement without measuring polarization. Likewise, the laser diodes have different emission spectra, they don't overlap. If does spectrometry without measuring polarization, she learns information about polarization by just seeing what color the photons are. So there is a side leakage shadow. Another example, a certain type of cryptographic protocol, the so-called decoy state protocol, needs Alice to emit signals of different energy. And again, the engineer tells you that the easiest way to make signals, two flashes of light of different brightness, is to use one laser diode and simply modulate the electrical current through the laser diode. So use one generator with different amplitudes of electrical current and one laser diode. And indeed, you get different pulses with different mean photon number, but the timing characteristics of those pulses will be different as well. So they will differ in shape and timing. And now if Eve sees a photon flying at this time, then she knows that this is 3 times as likely to be the brighter pulse. They are normalized, so this signal pulse is brighter. They have been normalized to the peak energy. So it's 3 times as likely to be this type of pulse than the decoy state of pulse. And if the timing is this, then this is most likely decoy than the signal state. And by the secret protocol, she should not be able to distinguish between the 2 types of pulses. So your secure protocol stops to work. It becomes insecure. And you come back to the engineer and say, look, what we have built has a problem. It has a side channel. Can we build a better source? And he goes, sure, yes, it's more expensive, but let's do it. Let's take one laser diode that emits a continuous train of pulses without modulating it, just a train of pulses. And then we take an electro-optic modulator to modulate its intensity or modulate its polarization. And because the act of modulation is physically separated from the act of generation, then hopefully there will not be a side channel. And if you characterize this type of source, indeed, you see that the signal and decoy pulses, this is intensity modulator, are almost perfectly overlapping. There are teeny discrepancies because your measurement setup is not perfect, but probably they are the same or very, very close to each other. So the problem seems to be gone. The next thing, you need to prove that your source is secure. So you come to a theoretician, the mathematician that develops your security proof, telling you what is your secret key rate for this system. And he has a perfect security proof for a system that has no side channel in the source. For a perfect ideal source, this is the key rate versus distance. So up to 140 kilometers of fiber for a particular QKD system, you can have secret key with this rate per bit. And you ask him nicely, can you extend your proof and incorporate those imperfections, this characterization result or those characterization results, and tell me what will be my secure key rate for this flawed imperfect source. And he tells, sure. He spends 2 years and comes up with a more complex security proof that can take your measurement data and predict the secret key rate. And he tells, look, and this is a very good source, but you have very teeny discrepancies. And my security proof, unfortunately, gives you a slightly reduced key rate. But still, it works up to 80 kilometers. So use the secret key rate, and you have proven that you are secure. So you'll find here. And you know, even if you have these significantly distinguishable states in the source, you can still get some key rate up to a short distance. So with multiple laser diodes, it still works, but not very well. But if you have this type of source, I'm sorry, you cannot get secret key at any distance, so I can't plot it. So this is the general approach. You discover an imperfection, you can characterize it, and then you can develop a security proof that takes it into account and calculates the secret key rate based on the measurement results, characterization of the imperfection. The tutorial part is done. Any questions so far?
No, not yet. So please continue, if possible.
I can take questions at this point.
Yes, please. Hello.
Yes.
Could you please repeat once more what you said?
Well, anyway, you can just proceed.
All right. Okay, now we talk about the recent research results. So, most countries that use cryptography, or basically all the developed countries, have formal certification procedures for their cryptographic equipment. So, any cryptography used in that country has to be certified for quality. So, it depends on the country. Some countries require certification for more users, some for less users, but certain types of use, for example, banking or government users of cryptography, require the quality certificate. And this certification system is well established. It has been in practice for a long time for classical cryptographic systems. And it works like this. The government, together with the National Security Authority, comes up with a legal standard or set of requirements that a cryptographic system should have a certain type. So, for example, RSA or AES or any other encryption type or an implementation one-time path, it has to be satisfy certain. It has to pass certain checks and has good enough quality. And the government accredits a lab that can do this quality check. The developer of the system or the manufacturer has to give a sample of the cryptographic system to this accredited lab, has to give internal engineering documentation, and this accredited lab typically spends a few months checking the quality of its implementation. One thing it checks that the specification of the system is correct. So if the system says that this is a BB84 protocol with decoy states, indeed, it will check that the system implements this particular protocol it claims and that it has the key rate and all the data interfaces are as described in the data sheet. So the functional check. And the other set of checks the accredited lab does, it checks that the system has sufficiently good countermeasures or stability against any known implementation imperfections. So any attack on this cryptographic system has to be counteracted in the implementation to a level of quality or level of strength prescribed by the standard, certification standard. And if it passes all the checks, the system gets a certificate, then it can be used, sold and used in that country. So this process is well in use for classical crypto. The Russian Federation, for example, has hundreds of cryptographic standards for different classical cryptographic systems and security systems. And now this is getting established for quantum key distribution. It's a new technology, so no country has established it yet, except perhaps Russia, but this is well in development. So the standards and accredited labs and the manufacturers of QKD equipment also need to prepare their systems for certification. And now, if a manufacturer has made a new cryptographic system, it's quite useless to simply submit it to an accredited lab and wait for a result. Because if you haven't checked as the manufacturer that your system has proper countermeasures, and you need to check first that it's going to pass the certification. So you actually need to take the standard and see whether it's going to pass the tests. Otherwise, you're making an expensive mistake. You are wasting a lot of money and time, and you will not get the certificate. So first, the manufacturer needs to do the homework. And for the QKD, because this system is only now getting established, the first step for any manufacturer was to examine their own system and do their own in-house analysis. And several manufacturers have involved an external analysis team for this part of work, preparation work, and I have been honored to be a part of this team for several manufacturers. One of them is ID Quantic. We worked with a Chinese manufacturer, Quantum CTEC. We worked with 2 Russian manufacturers. And now I'm telling you about the latest published work in which I participated with. This was the security analysis for one of the Russian QKD systems made by a manufacturer in Moscow, QOART. And this is a prototype of a high-speed system with 312 megahertz clock rate. And we had an international team with people from different countries that did the security analysis and checked everything about the system based on documentation and a sample of the system. So this is a typical prepare and measure QKD system. It has a laser clocked at 312 megahertz, and which just emits a train of pulses. It has an intensity modulator. So this system runs BB84 decoy state protocol. So it has an intensity modulator to prepare different intensities, and it also has a phase modulator, polarization modulator to prepare different 4 polarization states. So indeed, you can already see that this is a more secure source scheme with the laser separator for modulation. So good. Then these pulses of light, they pass attenuators with several tens of dB attenuation, that attenuate into a single photon level. They pass the isolators for protection against certain attacks, pass the transmission line, and go to the receiver Bob. Bob uses polarization modulator with 2 basis choices for 2 possible measurements, randomly chosen, and has a polarizing beam splitter and 2 single photon detectors. So he does one of the 2 basis measurements. There is also a synchronization channel, multiplexed at a different wavelength. For this system, when we analyzed the documentation, we have found about 15 potential implementation vulnerabilities. So we made a report to the manufacturer, and we also ranked the vulnerabilities and how severe they were. 4 of the vulnerabilities were confirmed to exist in the system, and they could also be exploited using today's technology. Means if that did not need future technology, you could simply buy off the shelf components and build and exploit. And indeed, those vulnerabilities had to be fixed. So the company came with, they implemented a countermeasure for each of those high-risk vulnerabilities. Without this, the system will never pass the certification. And for the remaining vulnerabilities, so this is what has delayed the publication of this report, and you can read about them in detail here. And for the remaining vulnerabilities, we recommended the system for certification tests. So let me show you some of those imperfections. So one important imperfection, when a system has single photon detectors, there is a known problem with detectors. They can be blinded and controlled by EVE using bright light from the communication line. And indeed, the detectors used in the system were blindable and controllable. But they also had a rudimentary countermeasure against this attack, a photocurrent monitor. And the photocurrent monitor actually triggers on a continuous wave blinding. So the most simple form of this attack is successfully detected. But we could still blind the detectors using pulse blinding, not continuous, but for a short amount of time, and still control it during the blinding periods. So they failed a slightly more sophisticated attack. So we recommended the company to update the countermeasure. They made a monitor with a much higher bandwidth, not still to be tested in the security lab. And also we characterized the detectors for superlinearity, which is a more subtle security problem. And the characterization results basically tell that you need an improved security proof. But this is the work in progress. Another important attack is a Trojan horse attack. In this attack, EVE can inject a bright pulse from the communication line inside the Alice. So she just injects a lot of light in the fiber, sends them towards the source. This bright pulse of light passes through all the components and reaches the modulators. So it gets modulated by the same polarization modulation and intensity modulation that is preparing the quantum states. Then components always have back reflections. So a small amount of this light behind the modulators will be reflected back and will exit back into the communication line. And if at least one photon gets reflected back, EVE can read from this photon what the state of the modulators was. So she externally interrogates the modulators. The protection against this attack is to have enough attenuation for this round trip light, so if cannot get much information out. And if is limited by the physics of single mode fiber in how much light she can put in. The fiber can carry a lot of light, several tens of watts, but its core is only 8 microns in diameter. So if you put above a certain amount of power in the core, the material ionizes. So the fiber physically explodes and it cannot carry more than a certain some tens of watts of fiber. So this is a physical limit on how much light you can inject. And if your attenuation is sufficient to attenuate that light to a sufficiently low probability of photon returning, then the key leakage is bound, limited. What makes it more difficult to characterize this attenuation is that if is not limited to your operating wavelength. She can attack at 1550 nanometers, of course, but she can also use any wavelength that the fiber can carry. And this can be anything from ultraviolet to beyond 2 microns. Fiber carries a very wide spectrum. So you actually need a very wide band spectral characterization of insertion loss of each component. And this normally you cannot do, you have to do it yourself, so we have to build a setup for this characterization. Another type of light injection attack is laser seeding. So he also injects light at a wavelength close to the laser wavelength. And she essentially seeds the laser cavity with external photons. And when the laser is pumped with current, those external photons get amplified. And this can change the timing characteristics of the laser. It can increase the energy of the emitted pulse, and it can also shift its wavelength if the seed photons are at a slightly different wavelength. So you hijack the emission mode. And each of those problems actually breaks security. So if should be protection against, again, the protection is to provide enough attenuation. So given the limit on the injected power, physical limit, not enough light reaches the laser to do any of the effects, harmful effects. Laser damage, another attack where if injects a lot of light towards the source. It's known that when you inject tens of watts, some watts or tens of watts of light, this large amount of light can actually damage the components. So physically melt and burn and make permanent changes to the optical components. If it's not supposed to do this, I mean, this should be a shielded box, but the optical input is open. So Eve can do laser damage. In particular, previous work has shown that when Eve damages the attenuator analysis setup, she can permanently reduce its attenuation. And then the system becomes insecure because Alice emits brighter states, multi-photon states in a line instead of single-photon states. If the attenuator is burned and become more transparent. To protect against this attack, we offer to insert an additional power limiter in front of Alice. It's an extra component that takes all the damage by itself and is always, under all circumstances, protecting the next component from damage. So it limits the amount of light passing it to a safe amount for the rest of the skin that cannot do laser damage. So protection component, power limiter. Another problem in the source is the imperfections in the state preparation. This is a high-speed QKD source. It's clocked at 312 megahertz, and because the electronics has limited bandwidth, the states, subsequent states prepared by the source are going to be dependent on each other. The theory requires that each emitted state is independent of the history of emitted states. But actually, it depends on the previous states emitted a little bit. So the so-called intrasymbol interference problem, the previous states affect the current state emitted. And this is a security problem. There is a security proof that takes into account this as an information leakage channel, and so this needs to be characterized. And this was my favorite problem. So when we examined this scheme, this commercial QKD system, we saw that it has some calibration algorithms, the extra algorithms that are not part of the protocol, but they are required for proper system operation. So it needs to set the working point or bias of the intensity modulator. It needs to set proper timing of the both modulators to correctly apply the modulation. It needs to set proper timing at this polarization modulator, and it needs to pick proper timing or time shift of each gate, both detectors are sinusoidally gated at a high speed, so it needs to align the gate with the arrival of the photon. And it does all those fine calibration algorithms by sending photons from Alice to Bob through the public channel. So essentially, and uses the actual photon counts to do all 5 calibrations. And we were horrified because Eve has full access to those photons, and she essentially can control the calibration outcome. She can simply set any value of the calibrated parameter that she wants. And we told, okay, this is a very wide open loophole, and you need to change the system so it doesn't do this. It doesn't do the calibration through the public channel. So indeed, 2 of the calibrations were removed, and another trick was applied here to make it insensitive to those calibrations being performed through the public channel. And indeed, in particular, this calibration of detector timing is a very severe problem, security problem, because it can make the gates of the 2 detectors separate in time. And this is not just a theoretical threat, it's a quite practical threat. In a recent study that was done on a different commercial system, not this one, but a different commercial system, this was shown to be a very implementable attack. So in this system, there are 4 detectors, so this is a passive basis choice, but otherwise it is similar to the system we consider here. Those detectors have 4 different gates, the timing of each needs to be calibrated. Ideally, in normal system operations, so if you consider only 2 of those detectors, H and V, the timing of the detector gates should coincide in time, so this is normal calibration that the system performs. But Eve can insert a switchable delay line in the communication channel, so she inserts an eavesdropping machine that simply switches, introduces at random a delay or not, doesn't introduce it. And if she switches this delay during the calibration algorithm, she can force the calibration algorithm to select a very different timing for the 2 gates. And now only one detector is sensitive at a time, and the other is not, and vice versa, the other detector is sensitive only at this time, but when this one is not. And then when the system goes into key distribution regime, after performing calibration, then Eve can also switch this delay for photons coming from Alice to Bob, and she knows that if the photons are coming at this time, that only one detector can detect them, so she knows the value, bit value. And if the photons are coming through a different delay, at this time, that only the other detector can detect them, and she again knows the bit value, without actually measuring the polarization of the photons. Simply switches the delay. And this is a very efficient attack, and indeed, if you see a fraction of the key that the system reveals on the public line for error rate check, you can see that if applies to this switch a pulse for the first 20 microseconds, she keeps the pulse at 1 time position, and only 2 of the Bob's detectors actually have most of clicks, the rest are dark counts. And when she flips the switch, only the other 2 detectors have counts, and the first ones only have a few dark counts. So she controls which bit values Bob receives without measuring the polarizations. The point of this work was that this attack was actually fully automated and a black box scenario. So this attack does not need access to the inside of the boxes, does not even know the exact content of the boxes. This machine is simply inserted, and it uses the classical traffic to select the timing and all aspects of its operation. And it's automatic, it's a push button. You install it, and it does all the tampering without human control. But it also shows this attack is dangerous. Again, so after this work with the QOART commercial system, we have come up with a composition of a certification lab, which test benches the lab should have that is able to certify the system. There are 5 test benches. One is wideband spectral characterization test bench for components. Another is detector testing, so detector control testing. You need to characterize the state preparation. You need to characterize detector backflash. This is another security problem. Detectors based on avalanche photodiodes, they emit a flash of light whenever they have an avalanche. This is a leakage channel that needs to be characterized, how many photons leak back from the detector's communication line, and a laser damage test bench to test the quality of your power emitter. One by one, some of the test benches I show you. For the wideband characterization test bench, we use a supercontinuum bright light source, several watt of very wide spectrum. So this is its spectrum. It's from 400 to 2300 nanometers. We place the component being characterized after the source, and we use two spectrum analyzers to measure the transmission of this component in a very wide spectrum. So one by one, you can characterize each component of the scheme for transmission in both directions. And this is the noise floor of the spectrum analyzers. If the component has lower transmission than the analyzers can see, we simply conservatively assume that its transmission is bounded by the noise floor. And this is a conservative assumption. We have demonstrated the operation of this test bench on an example of 3 different common source configurations. This is not a source configuration used in the QOART system. It's just a generic source configuration that can be used in any system. And we considered a Trojan horse attack against this source. So here inside the source, we have laser and we have modulators. So the target of attack are the modulators. If injects a bright light pulse and it passes through all components that are installed between the modulators and the line, light goes back and forth, gets reflected, gets out. And in this, the first common configuration, there are 2 variable optical attenuators and 3 isolators, and also a fiber coil. And we characterize the transmission of each one in a very wide spectrum. We added them together for the back and forth light propagation, and calculated the total attenuation of each Trojan horse pulse. And this white curve is the attenuation versus wavelength. And you see that at a certain wavelength, the operating wavelength is 1550. At 1550 nanometer, it has more than 270 decibel attenuation. But at another wavelength, at 1200 nanometers, it has much lower attenuation, about 170 dB. And if you look at a security proof that predicts the secure key rate in the presence of this leakage, then the security proof predicts much impaired performance if the attenuation is only this high. To get better performance, you actually need to be above 260 decibel. Then the key rate is almost as good as a perfect system. So we try to introduce an extra component, filtering component, dense wavelength division multiplexer. And this multiplexer, now the red curve, indeed improves the total loss around the operating wavelength, but it does nothing at 1200 nanometers. So the security is no better. And only when we use a better frequency filter, a fiber Bragg rating with a circulator, this is a broadband spectral filter, it increases the total loss at all wavelengths, and only this configuration makes the system secure. And this was a demonstration of this test bench. You can use it for any other type of attack that depends on the wavelength. Intensity correlations and intersymbol correlations in the source need to be characterized. And so we characterized intensity correlations in different intensity states prepared by this decoy state source. To do this, you simply take the normal source and you remove the attenuator that prepares single photon states, or simply set the attenuator at the minimum attenuation if this is a variable attenuator. And then the source emits not attenuated states, but bright light states that can then be measured by a fast photodetector and recorded by an oscilloscope. So essentially, your characterization equipment is simple. It's simply a photodetector and oscilloscope. And then you do all the processing of the recorded oscillograms to find how much intersymbol correlation there is between the pulses. This is an oscillogram that has 5 states emitted. A vacuum state, very close to 0. Decoy state, a signal state, a brighter state, and the decoy state again. The decoy states have to be the same, but already you can see that the peak power of this decoy state is lower than the other 2 because it was preceded by the signal state. So the energy clearly depends on the history. If we integrate the area under each recorded pulse, we get the energy of this state emitted. And if you plot the distribution of energies over many pulses, then you can see that the pulses that were preceded by signal state tend to have lower energy. And the other pulses that are preceded by decoy or vacuum state tend to have higher energy. So the mean of the distributions is not the same. We calculate the mean of each distribution, and if you plot this mean of distribution on this kind of a level on this diagram, so this is all decoy states, and those are decoy states preceded by signal. They are like 3% less bright on average than all decoy states. And the decoy states that are preceded by vacuum or decoy are about 3% brighter, higher energy than on average. You can plot and see different correlations as variations of the mean. And you can also look for higher order correlations for a longer history. So here you look at the two preceding pulses, and you see that the energy means continue to diverge. In this paper, we have up to 6th order of correlations measured, and they continue to diverge. So in this system, there are actually long-term correlations. Now, thankfully, there is a security proof that takes the correlations into account, and if you use those two order correlations in the security proof, this is the secret key rate you can calculate for this system. The proof is by Marcus Curtis group. Another test bench. The laser damage test bench checks the quality of the power limiter. I remind that this component has to protect the next component under all circumstances, only transmit power no more than the safe power for the next component. So to test this component, we have a high power source. It's a fiber optic amplifier, several watt continuous wave. Then we apply this light to the test component and monitor how much light has passed through. We also have a low power laser to monitor the forward transmission of this component and another set of power meters. And then you do the test. We apply higher and higher amount of power, up to several watt, to common fiber optic isolator. It's a chip off-the-shelf component that is used in QKD systems to protect against Trojan horse and other light rejection attacks. We see how well this component can protect against laser damage attack. And it seems this is a good candidate for protection because it does partially lose isolation under illumination, but it always has sufficient isolation remaining to protect the next component. So it doesn't go to 0, it goes to maybe 15 dB or more. And if you apply too much light to the isolator, it gets destroyed, so it physically burns. You see one decapsulated, it's just charred. But it breaks gracefully. It becomes very high attenuating component, so it simply breaks the communication line. And this is a safe outcome. No key leakage has occurred. All right, so we thought that fiber optic isolators are good candidates for protection until we tried a different wavelength and a pulse of laser. And if it's not limited to continuous wave 1550 laser, she can use a different wavelength and different lasing regime. So we took a fancy laser that contains a ring oscillator and 2 amplification stages. And in this configuration, the laser emits 360 picosecond pulses at 1 megahertz repetition rate and a power of 1.3 watt. So there's quite a high energy in the pulse. And in a different configuration, with the last stage replaced by chirped fiber Bragg grating pulse compressor, it emits less than 30 picosecond, very narrow pulses at only 17 milliwatt mean power. So under those pulses, 1.3 watt or 300 picosecond pulses, we test the same isolators, and we see that the isolators lose 20 dB of attenuation under illumination temporarily. This is reversible. And at the same time, they don't increase the loss. The loss is still low. Forward loss is still low. And if 1.3 watt is applied, then they lose more than 30 dB of isolation, and they gain a little bit of forward insertion loss, but it's still about 10 dB. So they don't seem to be such a good protective component under pulsed laser attack. The most interesting result was when we applied 30 picosecond pulses at 17 milliwatt. The laser lost 20 dB of isolation temporarily under only 17 milliwatt illumination. It lost 20 dB. and it remained virtually unchanged in the forward direction. So 17 milliwatt is low power. So clearly more study is needed in different lasing regimes. And the last attack I show, it's a new attack. So you remember that we had this laser injection attack when if seeds the laser at the same or very close to its normal operating wavelength, puts seed photons in the laser cavity. And now we try to do the laser injection attack, but we inject very different wavelength. We inject 1310 nanometer light into 1550 nanometer laser. At 1310 nanometer, the injected light does not get amplified. So the laser has no gain at 1310 nanometer. But a different physics happens. The 1310 nanometer light gets absorbed and it externally pumps the laser diode. So it helps to increase the population inversion. The laser is electrically pumped, but now it additionally has optical pumping. And this extra optical pumping actually increases the energy of a pulse emitted by this laser by as much as 10% at 1.6 milliwatt applied. And also, the external pumping changes the pulse shape emitted. So this indeed is a possible attack, and the protection against this attack, there should be enough attenuation between the line and the laser that if attempts to seed. Good. So if you are more interested to learn more about attacks, there are some resources you can look in. First is a very long review. It's practically a catalog of all the known countermeasures and attacks made by German Security Institute 2 years ago, with lots of co-authors all over the world. So if you want to see which attacks exist, you can check this handbook. 2 years ago, the International Standards Organization has published an international standard on how to test QKD system against implementation vulnerabilities. It contains more than 20 different test modes, and so it covers more than 20 different vulnerabilities. But unfortunately, this standard is not detailed enough. It contains a general description of the structure of the test setup and how you should proceed the test, but it's only a few pages. So the description is not detailed enough to actually implement the test in the lab. To implement the test in the certification lab, you need to develop detailed certification procedures. The detailed certification has already been developed in Russia and transferred to a Russian accredited lab. So Russia, I think, is the first country in the world that has implemented security certification for QKD. As of this year, I know that the Russian QKD systems have already passed or have been going through the government certification. All other countries are a little bit behind, but taking effort. In Europe, the European Union decided to make one certification lab for the entire European Union, and they funded a 4-year EuroQCI project to develop certification methodology. So now many labs in Europe develop methodologies for different vulnerabilities, and in 1 or 2 years, all this methodology will be transferred to one European industrial lab, probably in Germany at Thales, that will then certify quantum key distribution for all of Europe. And my research, I have 2 labs. One lab is in Moscow, another lab is in Spain, in Viga. The research center in Viga handles some of those development projects for the European certification. And speaking of Viga, we are a small research center that currently has 3 labs and 1 theory group. There is a fiber optic communication technology lab led by Hugas Binden and David Ruska. There is a free space and satellite communication lab with a ground station for satellites led by Antio Lamas Linares. There is a theory group by Marcos Corti that specializes on security proofs with imperfections, and my hacking lab. I have 2 labs, one in Moscow, another in Riga. And if you're interested in PhD or postdoc positions in Riga, we have openings, we are growing, so please apply. Send an email to me or to Marcos Corti. Thank you. Questions?
Thank you very much for your very interesting talk. Please, Professor Marklin, please.
Yes. first of all, thank you very much for the very clear and detailed presentation. I seem kind of have a conceptual problem, which you probably can clarify. I kind of see a contradiction. On one hand, you told us that quantum security should assume nothing about the possibilities of the eavesdropper. It could use any kind of technology and everything. On the other hand, when we think, it seems like in this field, when we think about the security of some specific protocol or specific realization of a protocol, you go through a list of possible attacks and you consider protection against each of those. So, yeah. So, how would you comment on this kind of contradiction, if it's clear what I mean?
Thank you. That's a good question. There is no contradiction at all. Because we have different, so for all the classical cryptographic systems, there are two kinds of problems. One problem is that the actual algorithm can be broken. The algorithm is not secure, or it's based on assumptions that you cannot yet crack it. So any classical cryptography we use today, it only lasts as long as you cannot have technology to crack it. So you can break the algorithm, but you can also break implementations. And if you look at the implementation vulnerabilities in classical cryptography, they also exist. So today we don't yet have a quantum computer. You cannot yet break RSA by just applying the factorization algorithm. This will be possible in the future, very easy in the future, but not today. And today you can break RSA through problems like timing problems or power consumption differences. There are attacks like this on RSA. There is a whole catalog of attacks on classical implementations. So there is this foundation of cryptography, the actual security of your algorithm, the theoretical security, and there are practical imperfections. And classical implementations of classical cryptography have lots of practical imperfections that they have to be taken care of. So this process of looking for imperfections, seeing which attacks are possible, what countermeasures have to be applied, this is a very well-established process. It has to be done for classical crypto. The quantum cryptography is different in that the algorithm itself is unbreakable. And this is the sole advantage of quantum cryptography. But this is a crucial advantage because it's a very big danger when the algorithm gets broken. So for example, in 1977, the United States needs standardized DES cipher, digital encryption standard. And this is a 56-bit symmetric cipher. And in 2005, in 1998, a specialized computer built by Electronic Frontiers Foundation did a brute force attack on this DES. And it broke the algorithm in 56 hours. Today, it only costs 100 or 200 euro. You can pay somebody who has this computer running in the basement to break your DES key. So it's available as a commercial service. Literally, there's a guy selling key decryption of DES on the internet for a small amount of money. Basically, just pays for electricity. So when you have an algorithm, the basis of your security gets broken and everything crashes retroactively. And this can also be broken by somebody who recorded this. So we have this problem that the traffic can get recorded, and then in the future, when you have access to decryption technology, you will decrypt everything. This is a very big danger in classical cryptography because your algorithm is not sound. It's risky. And indeed, you know that it's going to be broken. And this is the crucial advantage of quantum crypto. The algorithm is solid. It's based on the laws of physics. In implementation security, the story is the same. There are implementation problems. You have to check them, find all important implementation vulnerabilities. You have to build countermeasures. You have to do certification checks. So that aspect of security is the same.
Okay, thank you very much.
Yeah. So you can say that there is almost no improvement. All cryptography has implementation imperfections.
Right. So you are saying even after this certification, when you are sure that it's secure against some kinds of attacks, you can still invent new kinds of attacks, and that would be...
Yes, a risk remains. A risk remains that we have discovered 15 different problems, and we have certified those problems, right? So the certification passes, and then somebody comes out with 16th attack or 17th attack and says, "Oh, but this is something that I have just found that you did not certify the system for." And this is a problem indeed, and then you have to update the certification and make patches against this attack, and perhaps in a few years you certify your system, including those newly found attacks. But this is the same in classical crypto. Also, new attacks are found from time to time. Implementation attacks.
Yeah.
But implementation attacks, they are actually less dangerous than the breaking the algorithm, because most implementation attacks you cannot execute retroactively. They require real-time access to. If you cannot make the attack today, the opportunity is gone.
Okay,
So
right.
it's kind of for almost all attacks. It's future-proof. If you haven't done your Trojan horse while the photons were flying, you cannot do it 20 years in the future when you have a better Trojan horse. But if the algorithm has a problem, you can attack recorded traffic 20 years in the future, no problem.
I see. Thank you very much.
Yeah, so the implementation attacks are less dangerous in that aspect. But they're numerous, so there's a lot of work.
Okay, any other questions? Please, Rajit is ready.
Thank you for a very nice talk and very productive. First of all, apologies for the delay. Allow me to ask two questions. You have discussed fiber-based cryptography, quantum, but what about free space quantum cryptography? What are the prospects? This is the first one, very generic. And second one, could you please name the protocols relevant for free space quantum cryptography? All
right. The prospects for free space quantum cryptography are excellent. So basically, here you have a fiber optic line, and instead you replace the line with telescopes pointing at each other. If you have a bit of time, I can show you what. I probably have a few slides about that. So you replace your fiber optic channel with the free space channel. And this has been done with satellites. First, you can do point-to-point between two ground points, or just high buildings. So basically, you do like this. If you can see the video. So you can launch a satellite in a polar orbit, low polar orbit, and then you put a ground station. And when the satellite comes into view, you establish a free space link. And with today's technology, you can do 1 kilobit per second secure key exchange with your satellite. Essentially, your satellite is a flying trusted node. It does 1 key exchange. Then 40 minutes later, it's flying over another continent, and it's doing another key exchange, and then it adds 2 keys together, and now publicly announces the result over a radio link. And then the remote stations on different continents share a secret key. And one satellite can cover the entire Earth with a key distribution network. This technology is less developed because it takes effort to launch a satellite, but it doesn't have to be a big satellite. It can be a small satellite. A few years ago, China, actually 8 years ago, China launched a medium-sized demonstration satellite that had quantum key distribution and several other physics demonstrations. And now China has another satellite flying. Europe is launching Eagle-1, which is the launch, I believe, is next year. Canada is launching a satellite and will launch this next year. And several other countries are developing quantum key distribution satellites. Russia has launched 6U, 12 kilogram, 12 units, 12 kilogram small satellite, micro satellite to test acquisition point tracking and classical communication. And if Russia funds this further, they will be the next satellite that does QKD. China is very open. There were many experiments between the Chinese satellite and other countries. They did transmission between the satellite in Italy, they did transmission to Vienna, they did a transmission to Zvenigorod under Moscow with the Russian ground station. So Russia also had a ground station. Oh, this is the Russian ground station in Zvenigorod, by the way. Yeah, and he is 30-second time lapse. The ground station tracks the Chinese satellite during QKD. So the green dot is the tracking laser, beacon laser on the satellite, and this red traces the red laser pointing on the satellite. So they keep track of each other. Yeah, so the technology is sound. The same protocols are used. So in fiber, you use polarization encoding decoy state. In free space, you use polarization encoding decoy state. In free space, you can do longer distance because the free space link has different scaling properties. In fiber, because of constant fiber loss, the scaling is exponential with distance.
Yes.
So it very quickly kills your transmission. So 1,000 kilometers or a bit more than 1,000 kilometers, you got nothing. In free space, the scaling is better. It's polynomial or as the distance to the power of -2. So all the longest demonstrations of QKD have been over free space. It's almost 2,000 kilometers now.
Allow me to ask one more question related to free space quantum cryptography. What is the diffraction impact on your beam? Because it will spread along the distance, and what kind of sources are more practical? What I am trying to tell, is it Gaussian beam? It should be beam with topological charges and so on. What is I mean here? If you can comment on that.
If you do QKD between satellites or all your beam is in space, you can, of course, you use Gaussian beam. The Earth atmosphere has it broadens the beam because of atmospheric seeing problem. The same problem why the resolution of ground-based telescopes is limited. So the broadening diffraction of the beam is much more, several times worse than just for Gaussian beam, but it's manageable. And you can counteract it with adaptive optics. There have been demonstrations when you use adaptive optics to compensate for this atmospheric seeing problem. You can also do it in QKD. It's complex, or you can do without. You just have a higher loss. So indeed, those are all technological problems, but they're successfully tackled. I mean, we have multiple QKD sessions with the satellite. So you're asking all the right questions, but this is just technology, and it's already you can do QKD today with today's technology.
Okay, because I was thinking that when beam is coming from satellite to your ground station, then you will have more space due to the diffraction to detect the photons. I mean, area of detection will increase because you have diffraction.
Yes. So typical situation is that the distance and beam spread is so large that the receiving telescope only cuts you a small fraction of the spot, because the spot is typically like several meters, and the receiving aperture can be some tens of centimeters. More than practical. So you get a high loss. You can get 30-40 dB loss, but this is not a problem. If you run your 10 gigahertz source, you still got a kilobit of key out.
Yes. But again, I think this is what you have already informed us. This is the reference beam. So reference beam will indicate us where to put our detector.
Yeah, precisely. So a typical scheme has two beacons that allow to do real-time tracking. And the beacon light can also be used to do some compensation of atmospheric turbulence. So the scheme has, I don't know, I probably have a few slides, but let me not bog you down with details. No, sorry. Ask there should be another talk about satellite QKD.
Sure. Thank you. Sorry for that. Sorry for the delay and your patience. Thank you for your patience.
So what else I can show about free space? I'm not doing free space QKD. We did some security vulnerabilities, so the free space schemes also have implementation problems. We did testing, but you should ask another speaker, invite another speaker who will tell you about satellite QKD. It's a very interesting topic.
Yeah. I will I send you an email, and I think I have some questions, theoretical ones, but I need some clarification.
Sorry, I didn't answer the wrong question. You asked about the wavelength of the sources. So this is a transmission of the atmosphere. And indeed, the atmosphere has absorption lines because of chemical absorption, molecular absorption, and also it has relay scattering. But there are quite many windows, so you can use 1550, the same wavelength you use for fiber. It's one of the transparency windows. You can use several shorter wavelength windows. So typically, free space schemes use 800, 810, or 780 nanometer, one of those windows.
Okay.
And then we have good detectors, silicon photodiodes, that are better than indium gallium arsenide.
Yeah. Okay, thank you. We have a series of quantum optics and related topic seminars, so I think we will use that platform for remaining topics. So thank you.
Sure, ask somebody from QSpace. They will be glad to tell about their experiments with MOSI.
Thank you.
And what they are developing now.
Thank you.
So any other questions or comments? Well, if not, let us thank the speaker again. Thank you very much.
Thank you.